Professor SAULIUS JUODKAZIS is a distinguished figure in the field of nanophotonics. He is a professor of nanophotonics. He is a deputy director of the Optical Sciences Center and the director of nanotechnology facility at Swinburne University of Technology, Melbourne, Australia. Professor JUODKAZIS earned his doctorate in experimental physics and material science from a joint co-tutor program between Vilnius University in Lithuania and Lyon University in France. Throughout his career, he has held various tenured positions at prestigious institutions, including University of Tokushima and Hokkaido in Japan, Tokyo Institute of Technology, Japan, University of Bordeaux, France, and Vilnius University, Lithuania. He has an extensive publication record with around 1,000 peer-reviewed journal papers, reviews, book chapters, book and conference proceedings. His research is mainly focused on the application of light field enhancement principles and spectral control in various areas, including micro-optics, sensing, solid-state lighting, and solar energy conversion. Professor JUODKAZIS' notable contributions is in the development of three-dimensional laser printing with nano microscale precision using femtosecond lasers. This innovation finds application in optofluidics, micro-optics, optical memory, and photonic crystals. His current research includes exploring nano-textured surfaces for applications in sensing, bactericidal properties, and light harvesting, plasmonic light field enhancement with spectral control, with applications spanning sensing, solid-state lighting, and solar energy conversion. In recognition of his outstanding contributions, Professor JUODKAZIS has received numerous awards, including Swinburne Vice Chancellor Research Excellence Award in 2021 and 2019, the National Eureka Prize for Scientific Research in 2017. He is also an elected fellow of Optica, formerly known as Optical Society of America and SPI. And being in Europe, I would like to stress an important aspect of European leadership. Professor JUODKAZIS is a world leader in the field of advanced manufacturing and nanophotonics. In a European perspective, a leader is expected to create opportunities for his team members. And I got this rare opportunity to receive postdoctoral training from Professor JUODKAZIS' lab. And I have witnessed, Professor JUODKAZIS creating numerous opportunities for all his team members. He helps them to grow into future leaders. And Professor JUODKAZIS, in fact, has created next generation leaders in the field of advanced manufacturing. And on behalf of all the BIOS members, I welcome each and every one of you and Professor JUODKAZIS to this webinar.
Yeah, so thank you very much, Vijay, for kind words, and thank you for this opportunity to be on this seminar, which is making interesting weeks so far. And today, let's have a look at what is happening in the field of ultra-short femtosecond lasers, how we can use them for interesting things. And this is exactly what I want to focus, not as a review, but what is new, where we are going. So let's start having a look what is happening with the femtosecond lasers, how the power is scaling over the years. And then can we apply those lasers for something which is usually considered less practical for those new technologies? Can we fabricate large areas? Can we modify large volumes which are required for industrial applications? So have a look at those strange applications, so to speak. Can we use femtosecond laser machining for solar cells, which is seems unpractical from the first glance, but I will try to convince you otherwise. Can we make 3D micro-optics out of crystals? Would be also many interesting applications especially for nonlinear optics. And can we use direct write using ultra-short lasers just as nanolithography tool in 2D, on flat surfaces, or in 3D, in the bulk, in the volume of materials? So let's have a look at those things which are really emerging quite recently. And again, very good introduction. Last month, we celebrated another frontier of ultra-short science, attosecond pulses, which are even shorter than something we're speaking today. But this is a celebration of experimental efforts to create the shortest possible pulses. And those pulses are compressing energy in time. At the same time, another Nobel Prize went for quantum dots, where optical properties, material properties are different, and we can harness this in quantum dots. So if we combine these two, if we have short pulses and we have small space, so our photons actually can reach very astonishingly high intensities when we have interesting phenomena. So we can have tunneling ionization at the limit, and we use those ionization and control of it for practical applications in laser micromachining. The field of three-dimensional femtosecond laser fabrication, if it is polymerization, we can call it printing, starts in the last decade of last century. So it's a little bit of time already, but have a look how publications were evolving over the years. If we put femtosecond laser and fabrication, those keywords, to see what is published over the years up to the COVID times, we will see this plot. It started with the very ambitious goals to fabricate waveguides in glasses, to make optical memory, or polymerize some 3D structures. So 3D is always the keyword here. So you fabricate in the volume, it's already 3D writing. Also, what is interesting to say that some papers in Nature, they have this magical effect. So if you see that paper, even original work was done some years earlier, it actually promoted very much understanding that you can make 3D structures on nanomicro scales. The scale bar here is 2 microns. And what is more recent is another Nature paper where fabrication of the very efficient material removal was demonstrated using ultra-short bursts of femtosecond pulses. And this is very, very practical application. Why we have those femtosecond lasers is again celebrated Nobel Prize 5 years ago for chirped pulse amplification, which we're hearing last week in presentation about extreme science driven by lasers. So this is the same plot which we saw already in the series of seminars here. If we look for intensity, how it has evolved over the years, so chirped pulse amplification is starting this point. And this is driving intensities to high frontier of new science. At the same time, for material processing, we are very fine in this window, which is around 1 terawatt per square centimeter intensity per pulse to 1 petawatt. So this is 3 orders of magnitude, but this is where we can do basically anything with very different materials in terms of how we can modify them. If you take 1 microjoule energy and pulse duration is 100 femtoseconds, and we focus into 10 microns, which is very modest focal spot size, we're already reaching intensities of tens of terawatt per square centimeter is threshold which will make damage to any known dielectric transparent material. So you can turn any transparent material into material which you can modify. And this is example here with the sapphire. So we can pinch hole inside sapphire. We'll show it in next slides, more details about that. And if you look for the conditions, what is happening if we will take this 1 microjoule and we will deposit it into 1 micron cubic micron, which is small volume comparable with the wavelengths. So we reach the intensity, the precious energy in volume. This is force in per square area, so it is actually pressure. So we have pressures which are exceeding pressures which we have in the center of our planet, but this certainly is dynamic pressures which we can apply. Again, this is the tool which we can apply precisely, and we can modify material. What is also appealing that delivery of light is easy. It's not contact method. We can focus inside transparent material. We can focus on the surface, and we can playing with different focal spot size. We can really reach very different scales, and we can scan beam. We can fabricate different areas. We are reaching 3D capability. Throughput, how fast you can modify volume workpiece is already reaching large numbers, which are really knocking on the door of the practical applications. And resolution, which I also show in this talk at the end, really can be very high. So what is happening in those last 40 years when ultra-short pulses started to be used, and at first science, and still many good science is generated. At the same time, it's very, very practical. What we see that in the last 20 years, from 2000s, laser power is increasing every 2 years. It's doubling. So this is 1,000 times more average power from femtosecond laser source in 20 years. And what it means. Let's have a look at presentation. This is slides from presentation in Photonic West a couple of years back, where manufacturers of femtosecond lasers, they showed some recent tabletop lasers. It means not very big facilities. It's really practical, simple lasers. If we look for 1 millijoule laser at 1 megahertz frequency, this is here 1000. So it's reaching this intensities of 1 kilowatt average power. Another presentation from the popular vendor, Amplitude. Their line of lasers, femtosecond lasers, in 20 years made hike of average power from 1 watt to 1 kilowatt. I also confirmed this with Lithuanian manufacturer, Light Conversion. They are confirming the same trend. So it means that we really have the same scaling, which is doubling of power now, optical power in every 2 years for last 20 years. We know Moore's law from microelectronics, where chips are increasing, density of chips increasing on the surface of our electronical devices. Here we speak about photons packed in time. So photons packed in time, average power, is actually following the same Moore's law. Then we can really, the message is that we can really expect that it will make impact on society and how we are making things, because now lasers begin to be really affordable, and energy which we can use is not anymore very sophisticated. We have high power at average power. It means high frequency and high pulse energy. So now it's not serious slide, but look at this. So it's giving the message that now with the kilowatt ultra short lasers at high repetition rate, we can really begin to think about fast removal of large volumes. So it's we are speaking about cubic millimeters per second, and the burst mode of femtosecond lasers, which usually is a current trend, can help us. So large area patterning, again, it's not a problem anymore because we have high repetition rate and we can scan our pulses over the large area very fast. And that Nature paper, which I mentioned before in 2016, they actually reached that ablation rate, which is 3 cubic millimeters per minute. And this is typical machining, mechanical machining rate in high precision tool manufacturing. So this is rate which was already surpassed several times from that first paper. And now industry begins to be more seriously looking into ultra-short lasers instead of some mechanical cutting tools. Also, another appealing feature for femtosecond laser machining is that it's straightforward application. Basically, if you think it's microscope. We started to use microscope to observe things which we place on microscope stage. But now with the high power, we can introduce that light and we can modify. We can modify inside, we can modify on the surface, and I will show also that we can modify on the opposite side, and there are some benefits to do that. So if you focus your laser tightly, so you can also increase, you can have even higher resolution of modification when you use stable laser at the very tip of intensity. So this is a flat profile of intensity. If we are focusing in the volume, so we have ideal distribution of focal spots shown here. So we can material just at the very center, and it can really be sub wavelengths, so there is no problems with breaking diffraction limit for modification, because it can really be guided only at the high intensity profile. So what is happening with material when we deliver ultra short pulses? And let's have a look at transparent material, because this is where femtosecond laser machining is really standing out. If we are focusing to focal spot, we know what to expect. But when intensity is high, we're actually reaching the breakdown condition. We are creating plasma excited state with the free electrons. So this plasma state, it's kind of metallic absorbing material, which is created following pulse duration. So it's usually happening on the short times. And then material is modifying. You have all mechanical effects, all hydrodynamics is happening later when energy from electronic system is coupled to the lattice, to the environment around the modified region. So energy at first is absorbed and then into electronic system, and then after a couple of picoseconds, material starts to be modified. It means also that modification of material is really a kind of pure, so to speak, because material is not changing during energy deposition. It would be not the case if we are using even just longer picosecond pulses, and nanoseconds obviously even worse. So with femtosecond lasers, you can really make precise energy deposition. And the only place I show a few formulas, but this is really something extremely basic. So energy should be delivered if we want to modify material. So it's absorption coefficient alpha. So it will be linear. For transparent material, it's not very big number, so light is passing through. And then we should have nonlinear term, which is changing absorption. And the first would be 2-photon absorption in many possible nonlinear terms. Depends on intensity. That's why we call it nonlinear. And absorption, where we deposit energy, is depending on alpha, so it will be skin depth. It's just reciprocal to alpha. Alpha depends on imaginary part of refractive index, and square of refractive index is permittivity. So if we know permittivity, we basically know how material respond to the intensity which we are delivering. And there is an interesting point in terms of changing permittivity as we create free electrons and plasma, that when this term is approaching zero, so when A and kappa are equal, so real and imaginary part of refractive index, when they're equal, it's breakdown by definition. So this is zero. It's dielectric breakdown, runaway, avalanche, and so on, so which is not really controlled method of modification. But just before that, we have possibility to have epsilon near zero material which can absorb very efficiently light. The energy which we absorb, it also can be argued how we can calculate it. But it's very useful to calculate energy in volume, because usually we are modifying volume. If we are polymerizing, we're also delivering energy in volume and writing polymerized structures. So energy in volume, which is deposited, will be simply coefficient of absorption, the fluence, which we are shining on that spot, and also where we absorb, so it's skin depth. It's very easy to show just from basic rules of Drude model that those free electrons which we are exciting in the material, they are key to deposit energy. When their concentration is reaching critical concentration given by wavelengths of light, this would be the condition when energy absorption is saturated. So when we are playing with intensity in those conditions, epsilon near zero, in order to have the strongest energy deposition. So with the 3 orders of magnitude, which is very easy in terms of fluence, and this will be the same 3 orders of magnitude in terms of intensity, with a very simple tabletop, not expensive laser these days, we can actually make any transition we want in material. We can start with the solid state material, we can heat it up, we can play with the phonon properties and resonances. But then if we increase power, we can have melting, we can have evaporation, then it comes to ionization, and we can convert into plasma, dielectric, or metal without any big difficulty. So it only depends how much energy per atom we deposited. That's why I spend a little bit of time showing that energy deposition argument, energy in the volume, which actually we can also calculate very well when we know the tight focusing conditions. And usually we are not reaching self-focusing in many cases. So really we have direct writing. We deliver energy exactly to the point. And this is separate story, but I want to show that all those 3D polymerized structures, which we see many times these days, they actually fabricated at the intensities which are quite high. They almost half of the breakdown intensity when you make ionization of your polymer. You are writing those structures at 1 terawatt per square centimeter. So these are really intensities when we are delivering energy by bond breaking, by creating free radicals directly by light. We don't really rely on photoinitiators. We can use them, but if we don't use them, we are still able to do 3D fabrication, but this is a little bit different story. So now let's have a look what the kind of extreme energy deposition we can consider. So in those papers already some time ago, we showed that we can tightly focus femtosecond laser pulse of very modest energy, and we can create extreme conditions. So we create pressures which are estimated, you will see on the next slide, which are huge. Temperatures are jumping during them. You deposit energy to the electronic system, energy is then coupled to ions, and energy jump is extremely high. What is also good in terms of retrieving those modified phases and not damaging too much material around is that it's still comparatively small energy, which is quenched quite fast. And quenching thermal quenching allows you, with the fast cooling, to retrieve new material phases, which are, many of them are predicted in calculations, but it's very difficult to retrieve them to room temperature. With the fast quenching, actually, you can do that. And here it's an example of those first experiments. We took sapphire, we polished it very thin in order to make those tomography images, and then single femtosecond laser was modifying along propagation those micro volumes. Now, if you look inside, just let's appreciate those 3D renderings here of those images. So they are inside. They are modification of single shots. Resolution was not showing what is inside, but this is shown here. If we break sample, we will recognize that in the middle of the sample, and this is a real surface, just below surface on a couple of microns. This is focusing cone of tightly focused light. We are pinching a hole inside sapphire. Modeling was carried out for the conditions of energy delivery, calculated as spherical. So this is a radius with deposit energy. And then what happens with the pressure, temperature, and density in the first picoseconds is shown here. We have shock wave, which is pushing material. Young modulus, this is that dashed line. So it's the shock wave is actually exceeding strongly the Young modulus. No surprise that we have modification of material, of sapphire. On the longer time scales, we still see shocks propagating at velocities which are larger than sound velocity in sapphire, and we see the opening of the hole. So this is mass density. So we see the hole which is opening inside. So this is really correspond to experiments what we see. From calculations, we see diameters which are twice larger than those which we saw in experiments, but this is was good in terms of the understanding the qualitative picture, what is happening. What is also amazing, if you think this is sapphire, and sapphire is pushed out of the center, and this is amorphous part of sapphire, which is densified. So amorphous usually is less dense, but this is amorphous, which is densified because it's squeezed against the wall against sapphire, bulk sapphire. And we know that it's amorphous because we can wash out in acidic or basic solution. This is shown here. So that those those conditions which we create is really extreme. So we have a look, want to see what materials inside those tiny volumes. And this was done in Argonne in the United States. We measured X-ray diffraction from the layers of modified sapphire. And what we saw was very simple X-ray diffraction pattern, which was at first unexpected, because what we thought that we will see, it will be some strange phases of sapphire. Sapphire is gray lines, and so we thought some changes of those lines, they will be pushed out of the positions because of immense pressures. But no, what we saw was this experimental result is shown here. And this corresponds to very simple cubic structure. And that cubic structure, again, not usual, because this is correspond to body-centered cubic aluminum, which we don't have around. What we have around is face-centered cubic aluminum, which is a much larger lattice if you compare with the BCC. So this is high pressure phase of aluminum. But let's remember, we started modification of sapphire, not aluminum. So this is what is happening, that we are deposit energy, we create ionization of aluminum and oxygen, and then at the end we create the phases of high density aluminum. And the pressures you see here, they are huge, which are required for those BCC aluminum structures. They were predicted in some theory papers years ago, but in this work we showed that we can have them in small volumes. They are nanocrystallites of around 20 nanometers in size. This is cartoon picture what is happening once we ionize material. Triply or even 4 times ionized aluminum oxygen is flying from the explosion, central energy deposition site, and then it's thermally quenched. It's experimentally obvious that there will be some conditions that we capture this BCC phase. And it is around ablation site. To go to do this type of experiments in synchrotrons is not so easy and simple. So we looked how we can prove that ionization and decomposition of material with something more simple. So we took germanium oxide glass. And why germanium oxide? Because the ratio of masses is much larger. So separation during this explosion site, that movement, should be more efficient to separate germanium from oxygen. If you compare aluminum, for example, aluminum oxides, aluminum and oxygen, their masses are more close. So we fabricated some voids inside glass, and then we looked for Raman scattering. And we looked in the region where nobody usually is looking, because it's not interesting. There is nothing happening in glasses there. But in fact, if you really focus on modified area, you can see that depending on pulse energy, usually it's opening the size of the void, you will see that oxygen is in that void. So this is the proof that you can really, with the energy at deposit energy, you are cutting chemical bonds, and you are ionizing material. And then in this case, we saw oxygen in much more simple experiment. Just to finish this kind of exotic energy deposition scenarios, let's have a look at silk. This is biocrystal. You see it from X-ray diffraction. So there is very clear diffraction bands. So it's 85% crystalline material. Single femtosecond pulse at green wavelengths, which is transparent for silk, is making this strong damage. You can recognize those features here, and this is actually amorphous silk, which is, again, not existing if you don't quench silk at 10 to the power 5 Kelvin per second. So it should be very fast thermal quenching to recover amorphous silk. And that amorphous silk is having interesting feature. You can wash it out in water. silk is not dissolved in water, but that amorphous silk is washed out. So washing out of modified areas can be a practical tool. So this is one of, let's look at some applications. This was our earlier work when we saw that we can recognize modification by actually seeing, after etching, we're seeing the modified areas. This can be straightforward application for making microchannels. If you drive modification inside the sapphire with a certain pattern, then put into etching solution. Because of very high contrast ratio of etching, you can even keep very long hours until all the diffusional process of etching out happens. You recognize that you fabricate very nice channels inside the volume of sapphire. This was visualized simply by putting rhodamine and making confocal microscopy images. The same is true also for glass. Glass only has less contrast, so you see that those channels here of the spiral is larger than the center, because center was obviously etched later. So we filled with rhodamine, and this is showing the depths of the luminescence coming out of the 3D structure recorded inside the transparent volume of glass. This is my colleague's work from EPFL, Yves Bellard. He is making mechanical tools out of glasses, and this is almost unbelievable. This is glass. It's silica glass, which let's repeat it in one more time. So the stress in this region is reaching 2 gigapascal. It's basically the limit for glass. And glass is not breaking because all this glass was cutted by writing femtosecond laser damage and then putting in etching solution. Etching solution was removing all stresses, all cracks. So to speak, it healed the glass. There was no mechanical failure points. That's why you can, after femtosecond laser writing and fabrication, using wet etching, you can have those mechanical flexures really performing to the limit of material. These days, already 20 years plus, it's already 3D printing service. So this is from Aachen University. There is a spin-off company. You can send your microfluidic channel or some 3D design, and they can cut it out of silica glass or sapphire. This reindeer is actually having the moving legs because the precision of fabrication was such that you can really make exact mechanics, modification and washing out in such a way that glass structures are embedded into each other and they can move. It's just one example. Now let's go to something what is more interesting and what is our recent interest of using femtosecond lasers. We would like to make micro-optical elements for many good applications. One thing is bad about femtosecond laser machining, any laser machining, that usually it's not really optical quality surfaces. When you do ablation, it's always not to the high precision of lambda 10, lambda 20, which is required for optical demanding applications. One way to improve this is actually fabrication of on the backside of your transparent substrate. So LIBWE stands for light-induced backside wet etching. So this is exactly what is shown. So you are shining femtosecond laser pulses onto the interface of material which you want to fabricate and some 1 or 2 photon absorbing solution. We used acetone and pyrene dye. What is good about this focusing on the backside is that highest intensity will be always on interface. Even when you begin to ablate and cut your material, on interface you will have maximum intensity. If you are focusing on the front side, what will happen that the highest intensity will be lambda quarter. It will be reflected light, which is making interference and maximum just above surface, but not exactly on the surface. If you are focusing and light propagates from high refractive index to low, this is the condition which is required that you deposit energy exactly on interface. So this is very welcome for machining, but still, after fabrication, it's never perfect. So it's shown here, and sometimes we want to fabricate conical lenses, which are optical lexicons with the sharp noses. And how to do that? Because if roughness is not good and we want to anneal and make it smooth, what we can do with glasses, surface tension usually make every lens spherical, which is not ideal. But in crystals and sapphire, even with the high temperature annealing, and you see the temperatures here were running up to 1600, it's still 500 centigrades less than melting point of sapphire. So sapphire is not changing, but the surface is modified and changing. So it's getting more flat, as you will see in the next image. And this structure is big scale image of optical vortex generator, which is really structure with the steps after annealing. And after annealing, we can make those surfaces not really as ablated light scattering surfaces. Here is example of diffraction optical element. And along this scanned line, you can recognize steps. The design was to have 4 steps to create 2 pi phase change, and this is zoomed version after annealing. Ablation spot is shown here. It's really very tiny, tightly focused focal spot, was used to do laser ablation, and it was a micro nano rough. But after annealing, it becomes atomically smooth. You can recognize C-plane of sapphire, but what is important that the design height was not changing. It means that we can create optics, which is as designed with the steps, and it is atomically flat. Certainly, it's very first demonstration. You have the changes on the side steps, so it's something to explore more. But technically, you never can do similar things with glass, usual material for micro optics. So crystals here have really advantage. Okay, so this was one interesting thing in unusual, as I promised you to speak about unusual things. Now let's move to another topic. Can we fabricate, can we use lasers to fabricate solar cells, which is large area applications? And here we followed Sajeev Johns, who is one of the inventors of photonic crystal concept. He showed over the several years that light trapping for solar cells can be better if surface on the light harvesting surface is not flat, not random edged, but periodic. So we collaborate also with the group in Germany, which is making solar cells of the design which is used now to reach world record efficiencies. So at first we started simply with silicon. Can we make patterns which are periodic on silicon? So we coated chromium and we etched, we ablated with laser, and then we used plasma etching or wet etching to fabricate pyramids, which are periodic structures on the surface. After chromium mask is removed, we have black surface, which is good. It shows that light is not reflected and absorbed. So on the back side of solar cells, we have all electrodes collecting electrons and holes. But on the front side, which is shown here, we fabricate those patterns for light trapping. So we start with chromium. Single shot makes ablation, which is subdiffraction limited. And then we fabricate large areas with the design suggested by, given to us by Sajeev John. And then after plasma etching, we have nice pattern of pyramids etched on the surface below the opening of those holes in the mask. What is also good that even if you over etch, those pyramids are not disappearing or not damaged. They simply go deeper to the new level, but they are not changing pattern. Sometimes if there is no ablated spot in the masks, so this is what happens here with the pyramid looking upwards, but this is also exactly proving that etching below mask is not damaging the structure. So it's very welcome for large area fabrication. So this was done on real solar cells. So we used, instead of chromium, we started to use the alumina mask, which is dielectric, and it's better for surface recombination of optically created carriers in solar cell. And alumina is part of anti-reflection coating always on solar cells. So it was we use this as a mask. We ablate it. We do next step of plasma etching and then removal of the mask to have periodic structure. And this is the result which was verified in Germany, and then they verified in Caltech by independent measurement of solar cell. So this was from this part of the pattern. And we obtained 23% efficiency when the neighboring solar cell here without light trapping performs at 21. So this was very encouraging first result that light trapping, the periodic structure is really working nice. Why we need to do that? Why we need to use periodic patterns as shown here in this modeling of 1 cubic micron of silicon with a pyramid etched on the surface. So this is a FTDD calculations. So it's simply periodic boundaries in the plane. So it's an infinite solar cell, and it's very thin. It's 1 micron. And if we shine plane wave at 1 micron wavelength, which is close to the band gap, what we see, light intensity distribution just below the pyramid. You see the hotspots, those red points, where electrical field is 6 times larger. So intensity will be square of that. So it's 10 times higher intensity locally happens because of that periodic pattern. If we have random pattern, this is not really happening. And then solar cell can only perform at ray optics limit. If you want to break ray optics limit and to approach to fundamental limit of solar cell for silicon, it would be almost 32% efficiency. You need to break ray optics. You need to go in light trapping using wave nature. This was predicted by Sajiv John, and now the group in Germany is chasing this on their high-performing solar cells. When we started to write those masks for etching, what we also saw that at very low energy, we are not opening mask, but we are actually alloying silicon and chromium. And again, this is only one slide and just showing the invitation and capabilities. So if you have nanofilm placed on your substrate, you can actually make alloy between those two materials. In this case would be chromium and silicon. They have very different melting points, very rich possibilities for alloying. We are not investigating this at the moment. We don't know what alloy happened, but we know that it's not chromium. You can't remove it by chromium etch. And you apply etching. For example, this was plasma etching or wet etching. Those islands are surviving. So those islands, if you have a look, this is 200 nanometers. It's really patterning and alloying of materials, nanofilms on nanoscale. So this is an invitation to use this precise laser writer for creating new materials at the very threshold of ablation. Okay, so another topic, and it started as 3D polymerization, but wait, it is now. So let's have a look. Before, usually 3D structures, high resolution, 3D objects were fabricated in polymers, and everyone was kind of showing this. Now this field moved beyond polymers. You can start with polymers. You can put some precursors. You can put inorganic materials. You can put some dopants, nanoparticles even, to make some functional final devices. You can even decide what photoinitiator you want for easier 3D printing. And then you fabricate your structures, which looks like this in the center. But after you calcinate in oxygen flow or in airflow, you are burning all inorganic organic part, and only inorganic part is left. So this is changing shape this should be known and you can accommodate in your design. But if we look at the material properties, it's amazing. You start with the polymer. After annealing at high temperature, you can recognize Raman spectra of glasses, typical glass. You see the glass a little bit dark because carbon should be burnt and it's coming out of your microstructure. But if you continue with the conditions, time and temperature, you can begin to have material which is have different crystalline phases. You can recognize them. It's cristobalite in this case, also some zirconia oxide crystalline phases are created depending on the temperature. This is also simply to show the capability. There is no easy way how to fabricate this, and this is the one of the possibilities. Finally, can we use femtosecond laser as a nanowriting tool? Let's start from today. We have here a substrate with the this case, we can call it almost like resist. We shine femtosecond laser, but here is calculation in the corner. If we have air gap and around we have titanium, and this is polarization of light, this dashed line is showing the diameter of focal spots, let's say diffraction limit, and this gap is smaller. What is happening at the interface between titanium and air? Just from boundary conditions, we know that permittivity multiplied by electrical field, it's displacement. If there is no free carriers, it's dielectrics. So then on the opposite side, it should be the same for titanium. If I'm shining light, which I know from laser, so I have electrical field intensity defined. Air has a permittivity of 1. So in titanium, it will be low electrical field because titanium has permittivity refractive index square, which is almost 6 times. We speak here electrical fields, so 6 times difference of electrical fields, so intensity will be square of that. So 10 times and more intensity difference can be in the gap, and light here is, we calculate this for interface, but gap is very small. So light is kind of counterintuitively squeezed into low intensity region. It's not wave guiding, it's near field. So this light is not propagating, but it's really focused on near field. And what we can do with this light, we ablate a spot, as I showed in mask writing for solar cells. It's big hole. It still can be subdiffraction limited, but it's large object. It's hundreds of nanometers. But if we are very patient and we choose conditions at very tip of intensity, here it's my marker pointer here. I'm moving it out just to not block the hole. So if we ablate in 1, 2, 3 pulses, we can really ablate nanohole of tens of nanometers, and then we reduce pulse energy by 30%. It means it will never ablate anything nearby. But once we are on that goal, exactly for this effect which I just described you about continuous permittivity around the interface, we can use it as a pen. We can drive ablation and modification. We can steer it by changing the orientation of polarization, and we can really make nanowriting. So this is 2D. The latest is 3D case. This is still on archive. But hopefully it will be very soon published. So in this case, we simply prepared intensity, which is needle of light. It's kind of Bessel beam like intensity profile. So it's long light formed by concentrical type of grating on a space light modulator. So we are focusing this light inside glass crystal, and if we see at the threshold of damage, we recognize that there is some modification. But this is just to know that we can modify inside volume of transparent material, and this is obvious. But then if we scan our beam, the beam now propagates from the right to the left, and we are scanning out of the plane of the screen. So if we are scanning at very fast, let's say 10 pulses per micron, so we will have along the line some modification. But if we scan slower, less repetition, this is just so we are scanning beam and then overlap is stronger, we are scanning slower. What we can see that more and more those damaged areas are connected, but they are connected with the same widths into really nanoline, which is shown here. If we zoom in, and this is done by, after writing, you put your glass into etching solution just to visualize what is modified. And you can see that modification is really very well localized on nanoscale. What is the reason for this modification? It's exactly the same, which I spent a little bit of time explaining using 2D example. Once light is propagating and is modifying glass, modifying it means creating free electrons, ionizing it. So creating of electrons, reducing refractive index. Those regions with the lower refractive index are attracting, because of that interface between glass and a little bit reduced refractive index of the glass along propagation, light will be concentrated. Certainly, in this case, there is no very clear interface, but obviously the physics is the same. Light is trying to be in the lower refractive index part if there is very sharp gradient of refractive index. So this is the reason why we can concentrate light. That light is not propagating, it's not waveguide, because this is low refractive index, but it's because of that interface, localization of light near field is enhanced. So we can modify subsurface. Surface is not ablated. We are modifying with a Bessel-like beam inside the glass volume. Then it was polished to reach the modification area, and etching out in wet etching conditions was used to reveal the structure. And have a look. This is glass. This is really, when we saw first time, it was very nice and almost unbelievable. You can cut with laser by modifying those regions and etching them out. You can really slice glass. And this is a similar materials and dielectrics. Can you do this in very different materials? Optoelectronic crystals, such as the lithium. And it took some time, but this is from here. Have a look at YAG, at this ceramic material, which is sliced with femtosecond laser and then wet etched. Yes, some breaking was happening. Who is working with YAG should know it's very, very brittle material. But still, can you imagine? So we can cut really nanoscale structures out of crystals or dielectrics just by direct laser writing. So this brings me to conclusions. And what I showed was something which surprised us, that we can apply Moore's law for packing photons in time. It means average power. For femtosecond lasers, it's only for femtosecond lasers. The lasers are not following the standard. But femtosecond lasers, the photons really packed. There is technologies how to do that. And now we can use them really for practical applications. Large areas, okay, large areas at the moment, only 2 by 2 centimeters for us for solar cells. But again, if you think about solar cell and patterning surface to get dense, no complex deposition and lithography, right? So it's really practical and simple technique to fabricate large areas for efficient solar cell trapping and solar cells with the breaking ray optics, Lambert-Chian limit. They can perform at the maximum efficiencies. And this is very important for thin solar cells. I showed calculations for 1 micron, it's just calculations, but this separation of carriers is even better for very thin solar cells. So if we make light trapping using femtosecond writing, can be something practical. Then micro-optics out of crystals. Again, not the first idea you will try. You think that glasses is more easy, but if you want to fabricate very complex shapes which are not damaged by high temperature annealing, and then they are maintaining shape for optical function, crystals actually can be very useful. And the final 2 examples, 2D, just a nanogol, which was used as writing for 2D patterns on the plane surface. By the way, the group was also, this is collaboration with Jilin University, and the group was also showing that you can write 2D patterns on curved surfaces, not flat surfaces. With electron beam lithography, you can't do that, but with femtosecond laser, looks like it's possible. And the final thing, which is still in review, but it will be published probably this year, we hope, is that you can use nanoscale writing, which was improving resolution by 2 orders of magnitude and aspect ratio by another 2 orders of magnitude for current 3D machining by absolutely whatever is the technique. So here, femtosecond laser writing is really standing out as good tool. So with this, I should acknowledge collaborators, theory group, Bordeaux University, Australian National University, Vladimir, Eugene. It's our theory gurus. Our group members, engineers, students, and postdocs from recent years. We collaborate with Arturas from Stanford on X-ray diffraction and synchrotron characterization of those small volumes of modified materials. Sajeev John is guiding our solar cell project, what patterns we should fabricate. Some characterization, we collaborate with Japanese group, and yeah, I should say this team, Genzi Lee, he's the student, just finished his PhD with those amazing 2D and 3D nanoscale writing tools in the Gongbo's lab. And this is our funders. Thank you for your attention.